Welcome back to the workshop. We want to continue taking a look at section 6.2. So let's look at a couple examples, and then we're going to look at a theorem associated to those examples. All right, so we want to find the indefinite integral. No instructions this time other than find the indefinite integral. What we're going to do is we're going to use a couple substitutions to help us. The first of these two examples, I was going to say first two, but they're the only two. They're very similar to one another, but the first one is leading into the second one. So we will take a look at these in a moment. So if I want to find the integral of cosecant squared theta over cotangent theta d theta, a lot of times it's helpful. It's helpful to know the derivatives of the trigonometric functions, right? That's something that we took a look at in Calc 1. So if we return to our formula sheet, this is going to be very helpful. Being familiar with this, taking a look at this is going to help us out. I'll tell you, I gave an attempt at this problem and I didn't refer to this derivatives and integrals sheet, right? You might have a different version, but pretty similar. And when I approached this problem, I approached it in a way that made a lot of sense, but it was wrong. And then I made an algebraic mistake, and I came up with a fantastic answer that was very easy to come to, but it was wrong because I didn't think about this sheet, because I then made a algebraic mistake. Do they happen? Yes. The problem isn't that they happen. The problem is whether or not we can recognize them, recognize when we make these mistakes. So I was able to recognize it, and so I corrected it. And so I'm showing you the correct way to do things. And one of the things that we need to do is refer to exactly this, right? We want to keep these things in mind. So we want to remember that the derivative of cotangent is cosecant squared, the negative of cosecant squared. So when we see this, we see a function and its derivative in the numerator. Okay. When we have that, we have exactly the natural log. In this case, maybe a slight variation because, right, the derivative of cotangent is negative cosecant. So if we let u be equal to the cotangent of theta, then du would be equal to the cotangent of theta d. Sorry, not cotangent. I just said what the derivative is. It's negative cosecant squared theta d theta. There we go. So I can observe that here, with the exception of there's a negative sign missing. So if I rewrite this as the negative of 1 over cotangent theta negative cosecant squared theta d theta, then we can recognize that the negative and the negative would cancel. The cosecant goes in the numerator, and we have exactly what we started with. But this allows me to recognize that I have the integral of 1 over u du, the negative of that integral. And that would just be the negative of the logarithm, natural logarithm, of the absolute value of u plus c. Make our substitution back, so we have the natural log of the absolute value of cotangent theta plus c. And that's it. Okay. That's not horrible. It's just the biggest thing is making sure that you're familiar with our derivatives and integrals, right? When you're talking about polynomials, we remember those ones pretty well. It's the trigonometric ones that we don't recall. The other thing that we want to recall is not only the derivatives and integrals, but we should have a reference sheet on these relationships here. If I haven't already, I'll make sure that this particular pair of pages is posted, so that way you guys can familiarize yourselves with it. And I'll make sure to provide this on exams. I don't want you to have to memorize all of these things. You should be familiar with them. Many of these you shouldn't have to look up. If you're constantly looking these things up, you're going to have a real hard time. But anyway, we want to make sure that we're at least familiar. So then our second example, the integral of tangent theta d theta. Well, there's no quotient here. How do we handle that? There is a quotient here, right? Again, remembering what tangent is sine over cosine. So if we first recognize this as the integral of sine of phi divided by cosine of phi d phi, now we can observe the quotient. Furthermore, now we have almost the exact same thing as the previous problem, right? If we let u be equal to cosine of phi, we should recall that the derivative of cosine is negative sine. So du is negative sine phi d phi. And now we just have to introduce the negative sign. So negative of the integral of 1 over cosine phi, negative sine phi d phi. So we see that we have the integral of 1 over u du. We say, yay, we get to use the natural log. So this is the negative of the natural log of u plus c. And of course, we substitute back so that way we are in terms of our original variable. So the natural log of the absolute value of cosine of phi plus c. And that's it. Right, phi is just another variable. Theta is just another variable. They're both Greek letters. So I'm just trying to introduce some Greek letters for us. It is common to use theta and to use phi as representatives of angles, hence trigonometric functions of these variables. All right, so where does this lead us to? Well, we actually end up with, we can apply this same method to find this theorem, right? We already know the integral of sine and cosine because we know their derivatives, but then we just found the integral of tangent, and almost in the exact same way, we find the integral of cotangent. And then very similarly, we can find these two integrals here, okay? If we want to keep those recorded as part of our integral sheet, that's absolutely fine because yes, in fact, they are right here, right? The integral of sine, cosine, tangent, cotangent, secant, cosecant. That's what we just wrote down. Okay, that's what we included here. All right, that is the end of this section. So we'll go ahead and call that good for this video. I'll see you guys back in the workshop to start talking about section 6.3, exponential functions. See you in a bit.